All right, so we are now recording, and we're going to look at 3A, number 17. So let me get there. Okay. All right. So let me get my whiteboard. And we're looking at, and this is section 3A, number 17. Okay. And so on this one, it says the national economy shrank at an annual rate of 10% per year for 4 consecutive years. Okay, let me rephrase that a little bit. It says, as a question, if the national economy shrank at an annual rate of 10% per year for 4 consecutive years, then the economy shrank by 40% over the 4-year period. And basically, want to know, is this true or false? And the answer is going to be false. So it's not just as simple as adding or 10% with itself 4 times and coming up with a total shrinkage of 40%. Because the problem is the reference value changes every year. So at that first year, whatever the economy was, whatever that amount was, it shrank by 10%. So the next year, it's going to shrink by 10% again, but you're going to take 10% of a smaller number. And so that's the issue. It's not just as simple as multiplying 10% by 4 and coming up with 40%. So the best way to see this, I think, is just to come up with a number. So give me a second, because this one I actually have worked out. Just have to find it. That is, I computed the numbers already for 4 years, except I did it at 8%, not 10%. Okay, so I tell you what, we're going to use the 8%. Okay. Just for so I don't have to push the buttons on the calculator and eat up a little time. So I'm going to rework this problem a little bit. It'll be the same problem, just different numbers. So it's going to say, if the economy shrank, so I'm going to use 8%. And the result will be the same. It's not going to be as simple as just, in this case, 8% times 4. Which would be 32% in this case. And then we're looking for what the actual value would be. That number I don't have here. Let me 1 second. Give me 1 second. Maybe I'll just redo the whole thing. I guess I didn't have this worked out as much as I thought I did. That's not right. There we go. Okay. Now I got it. All right. So here's the problem with the numbers that I have here. So if the national economy shrank at an annual rate, so I'm just going to go economy shrinks at an annual rate of 8% per year for 4 consecutive years, then shrank by 32% for the 4-year period. All right, so statement. If economy shrinks at an annual rate of 8% per year for 4 consecutive years, then the economy shrank by 32% for the 4-year period. All right, so this statement is false. Just on a quick cursory look, it looks like it, seems reasonable that it would shrink by 32% just simply by going 8 times 4 is 32 and saying, okay, 32%. But again, the issue is your reference number is going to change every year that you're taking the 8% of. And now, so when you work this problem, it's going to have different numbers. Like, again, the one that I just called up here real quick was 10% for 4 years. But to get this problem right, you're going to have to figure out what the actual percentage that the economy shrinks is. And so here's a way to go about it. I just started with, a number. It could be any number. I just said, okay, let's let, as a for instance, the national economy be $1,000. Just nice round figure. All right. And so to figure out, it's going to shrink, in this case, 8%. So to figure out how much that is, that the economy is going to shrink, put the percentage as a decimal, 0.08, times our economy. And that's what you're going to, whatever this number is, you're going to take that away from 1,000. That is, you're going to take away 8% of 1,000, get that number, take it away from 1,000. And so when you make that calculation, that comes out to 920. And so that's what I mean by the reference number is going to change each year, because now so after 1 year, this is how much your economy shrank. So the second year, it's not going to be 1,000 that you're going to take 8% away from. It's going to be 920. And so it'll be 0.08 times 920. Okay. And so that comes out to 846 and 40 cents. So 846.4. And now, so the third year, that's an 846.4 minus 0.08 times 864.4. And when you do that one, you'll get 778.688. And so that fourth year, you'll have 788.688. Got a little errant mark there. We'll get rid of that. Minus 0.08 times 864.4. And that comes out to 716.39296. Now, we, of course, would we're dealing with dollars, so we round to hundreds place. But I'm going to leave the 5 decimal places there before I get to my final answer. But this is where we would be after 4 years. So now what we're going to say is, what is the overall percentage that the economy shrank? And that's where I'm going to do this. I'm going to take, this was where I hadn't actually wrote this down. But I'm going to take 1,000 minus 716.392.39296 and divide that by 1,000. So 1,000 minus 716.39296 and then divide by 1,000. I'm going to get about 0.28360,704. Okay. And it tells you to, when you type in that percentage that the economy shrinks, and it wants the answer as a percentage, round to the nearest tenth. So to the nearest tenth, and the percentage would be about 28.4%. And that's actually how much the economy shrank. And so again, the calculation would be the same. I'm looking at this one. It says 10% per year. So you could again use 1,000 or whatever number you wanted to start with. And then what you would be doing is each time take your number here. Let's say 1,000 minus 0.10 times 1,000. Get this. Take whatever that value is, and then again do it 3 more times. And then when you get to where the economy is, to figure out the percentage that it shrank, you're going to go 1,000 minus whatever your value you have here, divided by, again, where you're starting, which was 1,000. And that's going to give you your percentage. All right. Oh, no. Let's see. Hold on a second. You probably didn't miss anything. I am very bad about transposing numbers. And so let me go back and look at what I did. So again, I'm copying this from where I had written it down. And then I actually kind of didn't write in these calculations. This would have been the correct number here. That one, boy, I told you I am not feeling good today. So all these numbers down this column here are accurate. Probably would have written these incorrectly had I been calculating it and not copying it down. That should have been 846.4, same as this one. And then this number right here was, and I don't even have an explanation why I wrote that. Because last year you're calculating 778 and then take away 8% of that. So that should have been 778.688, decimal point right here. But I do know these numbers are correct. And that when I had worked out this problem previously and had it written down here, this was the actual percentage. I mean, if you take 8% for 4 years from your national economy, you're always actually going to shrink to this value right here. Okay, just making sure no one else had chatted anything in. No. Okay, sorry about that. Again, I'm bad about transposing. Something I have to really watch myself doing, as you saw. in action. But any questions on this one? Are we good? Okay. Okay. Are there any other questions? Okay, so if not, then I'm going to go ahead and talk about 3C. So I'm going to turn the page. All right. And this up here. This is titled section Dealing with Uncertainty. Uncertainty. Okay. Okay. So, beginning this section, I thought this was probably fairly appropriate. We talk about uncertainty in numbers. It's talking about our national debt, um, which kind of as far as a local thing, obviously, it's oh shoot, I can't remember what the federal agency is now called, but back when I was a youngster, we just called it was just called the Bureau of Public Debt. Um, Now it's got a much longer name, but of course downtown, a couple different buildings, and that's what they do. They actually calculate our debt. Um, and so it talks about in 2001 that up to 2001 we had shown a surplus in our national budget. That is, we took in more money than we spent for, and that went in for about 4 years. And so they had calculated and projected that the surpluses would add up to almost 5.6 trillion over the next 10 years. Um, but as we know, that vanished, and we actually, I think we took on, let's see, what, $9 trillion in debt. So, so the difference between the projection and then what actually happened was about $15 trillion, which I mean, I can't really wrap my head around that much money. That is a lot of money. But to put it in perspective, um, about basically $50,000 for every human being in America, that is a citizen. Um, so that's a pretty good chunk of change. Um, but uncertainty in numbers. We predicted it was going to be this, and it turned out to be something far, far different. So, um, so we're going to look at terminology that we use and dealing with numbers. And so the very first thing we're going to talk about significant digits. Significant digits. And this may be a phrase that you have heard before. Um, so what we really want to know is when is a digit, we have 10 known digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Right. So when I look at any number, whether it's in decimal, it's a decimal number or not a decimal number, we always want to be able to look at it and say, okay, this is how many significant digits actually exist here. All right, so let's kind of summarize it out. So for any number, non-zero numbers, um, non-zero digits, that is 1 through 9, are always significant. Right, so there's never a case that they're not. Any non-zero digit is significant. So if I had the number 5,678, it would have 4 significant digits. All right. Zeros. So really, at that once we say all non-zero digits are significant, then that leaves one other digit, 0. So it's really now just an issue of deciding whether in a number 0 is significant or not significant. So zeros that follow a non-zero digit and lie to and lie to the right of the decimal point are always significant. Okay, so let's do a example. Um, all right, so again, zeros that follow a non-zero digit. So if you write your number down as 4.20, that's the number you see. Okay, so it is what it follows a non-zero digit. The zero follows a non-zero digit, and it's to the right of the decimal point. So if you're given a number and it's stated as 4.20, you're going to say 3 significant digits. Um, or uh, here's another one, 3 significant digits. All right. Oops. Okay. Yeah. So again, to the right of the decimal point, but um, and the zeros after the last non-zero digit, and to the right. Okay. So now zeros between non-zero digits. Or other significant zeros. Are always significant. Okay. So, again, let's do an example. 5,002. Right, so these two zeros are in between two non-zero digits. So there would be four significant digits there. Or if I had 3.06. Or if I had 30.0. So the deal here is this zero. This is where it's tricky. Because we're going to find out, like if I have the number 30, just 30, there's only one significant digit in 30. That's the 3. We'll talk about that in a second. But since I'm listing out to tens place here, the 0, and it's to the right of the decimal point, then that makes this significant, and so therefore this one's going to be significant. All right, so there'd be 3 significant digits there. Okay, so I've listed out our 3 cases where we're always significant. And again, what we're seeing very quickly is it's 0 is the one issue we have to kind of pay attention to. When is it significant? When it's not. So here would be the cases where we are always significant. All right. Now, zeros, I'm going to put a line here, kind of separating. Zeros to the left of decimal point. All right, so that would be that way, to the left of a decimal point. All right. Well, shoot. I didn't really say that accurately. To the left of the first non-zero digit. All right. Which may end up being to the left of decimal point. But zeros to the left of the first non-zero digit are never significant. Okay. All right, so what might kind of numbers those be? 0.006 has one significant digit. Again, these zeros are to the left of the first non-zero digit. So there would be one significant digit in that number. Or 0.00052. There would be 2 significant digits there. But again, these zeros are to the left. Okay, so, all right, now that leaves one last case. I'm out of room here, so I'm going to turn the page. And so the last case are zeros to the right of the last non-zero digit. But before the decimal point. So, are not significant. So I'm not saying never here. I'm just saying they're not significant. So I didn't say never. So I'm going to say this, unless stated otherwise. All right, so examples here. 50,000. All right, so these zeros are before the decimal point, which is right there. But they're what? To the right of the last non-zero digit. So unless someone says, hey, these zeros are going to be significant, we would assume there's one significant digit. It is possible they could be significant, but it has to be stated as such. Or if I had just 210, there would be two significant digits, again, unless otherwise stated. Right. So that is our um, uh, rules for significant digits. Now, what I want to do, give me 1 second here. I'll pull up a couple of the homework problems dealing with significant digits. Let's see here. So it looks like about number 7. All right, so from the actual homework, number 7. Okay. This one actually deals with precision too, though. So, before I can do number 7, I needed to define the difference between accuracy and precision. So, 2 terms. Accuracy, and I'm missing a U here, so I'll put it in there. Not great. Just let me rewrite it. ACCU. Man, I really can't spell today. ACCURACY. It does not have an accent. All right, 4 times a charm. Accuracy describes basically how close a measurement approximates a true value. Okay? A measurement approximates a true value. Okay. I got to throw this in there. So I'm going to say an accurate measurement has a small relative error. Now, you recall from our previous work with percentage, when we're dealing with relative, that we were talking about measurement in terms of a percentage. Okay, so we'll go back and we figure up our relative error in the same way we were figuring up relative percentages from the last section. All right, now precision, the word precision, and so how we're differentiating that from accuracy. Precision describes the amount of detail in a measurement. Okay, I'm missing an E right there. All right, in a measurement. Looks kind of sloppy. Measurement. Okay. So when we talk about precision, we may like a scale, weights, weight something we would weigh something with, and we may say, okay, its precision is to a tenth of a pound, as an example. All right. So, and that's how much detail we would have within that particular measurement. So accuracy is how closely a measurement approximates a true value. And precision is just the amount of detail that we actually have in the measurement itself. Okay. All right. So now I could, and let's talk about relative error real quick. And it's the same kind of deal as what we had looked at again in the previous section. We talk about absolute error. So just the absolute, when we talk, and I'm not going to write this one down, but absolute error is just your measured value, whatever that is, minus whatever the true value is. It's just take that subtraction of measured value minus your actual value. And then your relative error is then that measure your absolute error divided by the true value. So again, your measured value minus your true value divided by the true value. And then generally we convert that to a percentage simply by moving the decimal place to the right twice. And then we've got it per 100. So now I'm at a point I can go ahead and look at, again, on the homework, this would be number 7. Right. So state the number of significant. So this problem just simply says state the number of significant digits and the implied precision of the given number. Right. So the number given is $2,178 per acre. So this may be, what the price is for a piece of land. It's going to go at $2,178 per acre. So first off, how many significant digits? Hopefully you quickly said 4, because all non-zero digits are significant. So 4 significant digits. All right. Now, the second, so there are 4 significant digits. So I'm going to put 4, I'm just going to abbreviate significant digits. Now, on the precision part, the question it asks, what is the implied precision of the number $2,178 per acre. You're given 4 choices, multiple choice. And so I'm just going to read through the 4 choices real quick. The number is precise to the nearest dollar per acre. Second choice, the number is precise to the nearest $10 per acre. C is the number is precise to the nearest $100 per acre. And the last one is the number is precise to the nearest cent per acre. Now, the answer is to the nearest dollar, right? That's this. So to get an idea of what it would be if the answer had been the nearest $10, you may have had 2,170. Now so that would be to the nearest 10, where again this 0, unless otherwise stated, is not significant. So if it was nearest 100, it may have looked like this. And if it was to the nearest cent, it would have looked something like 2178. We may have gone 0.0, and there would have been an answer that would have been to the nearest cent. But it was given in this way here, so that's to the nearest dollar. All right, on your precision. That's number 7. All right. So let's look at the next problem, number 8, which gives you a different kind of number, but it's going to be the same kind of question. So I'm going to flip the page. Number 8. All right. You're given number in scientific notation 1.653 times 10 to the 4th. Okay. Now, recollect what you do if you wanted to put this into standard form is, since it's 10 to the 4th, that means that number, first off, is definitely bigger than 10. Move the decimal place, 4 times. And this kind of, I always said it really helps to actually put a number in scientific notation, and it kind of tells you how many significant digits you have. This is moving that decimal place 4 times. 16530. So I went 1, 2, 3, 4. And this would have, again, by rule, that 0 is not significant. So there are 4 insignificant digits here. All right. The precision here, and this was a measurement in seconds. So it's seconds. But precision would be to the nearest 10 seconds. And again, the reason being, is this 0 right here is not significant. So we moved to 10's place. So this would be, our precision is to the nearest 10 seconds. To the nearest 10 seconds. All right. There's another one kind of like that one. Well, let's back up. All right, so I'm going to look at number 10. Okay. We're going to carry out the indicated operation that's given, and we're going to give our answer to the specified number of significant digits. All right, so this one is 41 times 32.5. Okay. Now, and then we're going to talk about operations in general, because we're told here how many significant digits that we're going to round this one to. All right. So if we go and get a calculator, and you can just use a calculator if I can find one here. So take a calculator and actually punch it up on the calculator. So 41 times 32.5. Now, this comes out to, first off, on the calculator, 1,332.5. Now, it asked us specifically to round this to 3 significant digits. We're asked to round or give answer. Let's state it that way. It's not round this. We're going to give answer to 3 significant digits. So if I give my answer to 3 significant digits, then it would be 1330. Right? So, and so that I do have just 1, 2, 3, and again, remember that 0 after my last non-zero digit, but before the decimal point is not significant. And so I would just have 3 significant digits there. Any questions on that one? So let's look at another one. So number 11. All right, so I've got 270, and I didn't write down the 7. 274.23 divided by 0.087. All right, and we're going to give answer to this time 2. Significant digits. All right, so so if I punch in 274.23 divided by 0.087, now I come up with 3152.068966. All right, that's what pops up on the calculator. All right, but I'm only wanting to give my answer to 2 significant digits. So I'm going to round this to basically 3,200 so that I only have 2 significant digits. Questions on that one? Give me a second. Okay, well, so I mean, I'm not. in terms of if we're asked to give the answer to two significant digits, then in my answer there can only be two significant digits. So the question is, how do I round? How do I, give the answer that it only has, and as closest to this. So like here, it's not so much I'm getting rid of them per se, as much as when I look at this and I start counting significant, 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 that's three significant digits. Now, if this digit right here had been 5, 6, 7, 8, 9, I would have actually answered 1, 3, 4, 0. So remember, this 0 after the last non-zero digit is not significant to the and before the decimal point. Same deal here on this one. I'm just going to, so I might say I want to give a rounded answer to such and such number of significant digits. And so I start, I was saying, well, then I'm only, I'm going to round this. So it's not saying the hundreds place or thousands place, in this case, hundreds place. It's saying just two significant digits. So if I had been asked to round this to three significant digits, my answer would have been 3,150. If I had been asked to give this to one significant digit, then my answer would be 3,000. So it's not, it's just being able to take a number and rewrite it with the specified number of significant digits. And really what we're getting at here is just understanding when is a digit significant and when is it not. So, and that takes a little practice. All right. Now, in general, when you are doing arithmetic with measured numbers, so if you're adding and subtracting, then you round your answer to the same precision as the least precise number in the problem. Now, which means in this case, as an example, if I have 21.56 plus 42.8. Okay, now 21.56, I'm just punching up on my calculator, plus 42.8. Now, that actually comes up to 64.36. But since I'm adding, again, adding and subtracting are two sides of the same coin. Subtraction is defined as addition of the opposite. I would actually give my answer here as 64.4, right? And the reason being is I give my answer if I'm dealing again with measured numbers that had represented measurements, then I want to give my answer to the one round to the least precise. This was to hundreds. This was to tenths. So I round my answer here to tenths place. So when adding and subtracting measured numbers representing some type of measurements, I give my answer to rounded to the least precise, whichever number in there was the least precise. And so that's the rule for addition and subtraction. Now, multiplication and division, I'm going to round my number to the number that has the fewest significant digits. That is, my answer will have the same number of significant digits as any one of the numbers I was calculating with, whichever one had the fewest significant digits. Okay, so now, bearing that in mind, always remember, don't round until the very end of your calculations to avoid round off error. All right, so All right. So, but again, for adding, subtracting, round to whichever number in there had the least precision, then your answer will be rounded to that. If it is a question of multiplication division, then whichever number had the least number of significant digits, then you will round your answer to that number of significant digits. So it'll have the same number, your answer will have the same number of significant digits as whichever number you were calculating with had the least number. So those will match up. All right. All right. And two types of errors we need to go over that can happen. That is two types of errors you can encounter with numbers. There's basically random errors. And there's systemic errors. And honestly, to me, I think it's right in the term name what the difference is going to be. So you are measuring something out, perhaps, and there's just random or completely unpredictable events in that measurement process. Now, systemic errors are defined to be when there's a problem in the measurement systems that affects all the measurements in the same way, such as making them too low or too high by the same amount. And now, and that, let's find a problem. Okay, so I'm looking at number 13. And number 13 deals with random and systemic error. So that's a kind of a real world situation looking at the difference of the two. So number 13 says a tax auditor reviewing a tax return looks over several kinds of problems, including one, mistakes made in entering or calculating numbers tax returns. So, I mean, you just make an arithmetic mistake somewhere, and then of course your numbers are off. And then two, places where the taxpayer reported income dishonestly, so made a conscious decision in terms of the number they put in there that they were using wasn't correct, and it was on purpose, and that does happen. So now, question: does the mistakes in entering or calculating numbers, just mistakes made, those kinds of entering in numbers or calculating numbers in tax return, involve random or systematic errors? Well, that's random. And we call that a random error. It was an unintentional mistake, which are unpredictable and random. So you don't know when they're going to occur. I mean, it's just boom, we make a mistake. But where a taxpayer reported income dishonestly, that's systemic. Because generally, what we're doing there is we're underreporting our income, so our tax burden is less. So, that in this, as an example, and they will, don't think you'll ever get away with that kind of thing. I only got caught with it once, and it wasn't error. It was just years ago. I did some work went to a conference, and I was paid a stipend. And the issue was that stipend, and it was written from the state of West Virginia, um, um, but there was no deductions made. Normally, with all my paychecks, or any kind of paycheck. I remember the first paycheck I ever got, long time ago. I cooked at a restaurant called The Point of View, and as a teenager, and I get my very first paycheck, and I was looking over the check, and I'm like, "Who's this Spiker person, and why are they taking my money?" Um, so I was learning about life. But anyway, I got this stipend that it wasn't a huge amount of money. I mean, it was like $1,500 or something, but there was no no deductions made for tax purposes. And I just, I cashed it, and I forgot about it. And so, income tax season comes around, and I fill out my tax forms. Never reported that. But so after I submitted, IRS got back to me and was like, "You owe us some more money." They caught it. I mean, they knew it was reported to them that I had made the money, and so I wrote the check that I should have. But again, it was an honest mistake. I don't try to cheat on my taxes, but that would be, it was a random error. So kind of showing you the difference there between random and systemic. Okay. All right, so let's look at number 14, which is going to kind of deal with absolute and relative error and calculating each of those. All right, so move to number 14. All right, so let's say your true height is 73 inches. So 2 slash marks represent inches, which is 6 feet 1 inch. But a nurse in your doctor's office measures your height at 72.5 inches. Okay. So we want to calculate absolute error and relative error. Now remember, relative error is going to be a percentage. Okay. So again, your absolute error is going to be your measured value minus your true value. So in our case, our measured value was 72.5 inches, and then we're going to subtract 73. All right, so that's going to come out to negative 0.5. All right, so that is my absolute error right here. Now, your relative error, I'm going to abbreviate that, REL dot, relative error, is always going to be your absolute error divided by your true value. Or basically measured value minus true value divided by true value. So for us, our relative error will be that negative 0.5 divided by 73. All right, now that comes out to negative 0.007, which then, in terms of a percentage, is negative Okay. All right, good there on calculating absolute error and relative error. All right. Let's do another one. Dealing with accuracy and precision. Let's get a better handle on again. Just remember, accuracy describes how close a measurement is, how close a measurement approximates a true value, and precision is the amount of detail in the measurement itself. So, let's be problem number 15, dealing with accuracy and precision. All right, so your true height is 62.7 inches. All right, so that's your true height. All right, so true height is 62.7 inches. Now, you've got a tape measure. And this is standard for tape measures. It can read to the nearest 16th of an inch. And that's fairly standard for tape measures. All right. And actually, I might change the numbers up a little bit here, so I'm not having to do the calculations here. Sorry. Let's say we're going to go 59.5. That's your true height. I'm going to change that too. And the tape measure can read to the nearest 1/8 of an inch. And gives your height that is, so your tape measure reading gives your height as 59 3/8 inches. Right. So it's definitely, because this was 59 and a half, and so it definitely was close, but it was not right spot on with the true height. Now, got a laser device, and that should be an E, laser device. Gives readings to the nearest 0.05 of an inch. And it measures your height as 59.9. Should be a 9. That's 59.9 inches. Okay. So your choices here, we want to know which one is more accurate and which one has more precision. It may be that one has both over the other. It may be that the tape measure is more accurate and the laser is more precise, or vice versa. So we want to figure that out. Okay, so first thing we're going to do is talk about accuracy, how close we are, how much it approximates true value. So we're going to look at the absolute error. So remember, that's going to be our measured value minus the true value. So if I look at the tape measure gives your height at 59 and 3/8. Right. So the first thing I want to do is rewrite that as a decimal. Since my true height was in terms of a decimal. Or you can convert that to a fraction and work with fractions. Usually people like to work with decimals. So if I go with 59 and 3/8 and convert that to decimal form, and then you just punch that on your calculator, and to get that, it's going to be 59.375. Which means 59.375 minus your true height of 59.5 comes out to negative 0.125. So that is our absolute error there for the tape measure. Now, if I do the laser device, that was 59.9 minus 59.5, your measured minus your true, which is going to come out to 0.4. Now, here's where you can really see that term absolute and where it's going to come from. If I've got now, take the absolute value of each, so I get that non-negative result. So absolute value of negative 0.125, which would be 1.125, is less than the absolute value of 0.4. So the tape measure was more accurate. That is, it had a smaller absolute error. That's how we figure it up there. So the tape measure is more accurate. Now, in terms of precision, that's again how we're measuring. So since that the tape measure, so we'll put here the tape measure, we figured out was more accurate. Now, in terms of precision, the tape measure was precise to the nearest what? 1/8. Right, that was given right there. And 1/8 as in decimal form is 0.125. The laser, in this case, was to the nearest 0.05. Okay, so now and 0.05 is less than 0.125. So in this case, the laser is more precise. So your answer there would be the tape measure is more accurate. I gave you a more accurate reading, but the laser is actually more precise. Any questions on that? All right. A couple more like that. Okay. So I think I have gotten through everything I needed to get through here in this section. All right. My voice is just about left me. I don't know if you know, I'm for whatever reason, I'm kind of losing my voice here a little bit. At least it's getting kind of raspy. Any questions from anything we looked at? All right, so I am assigning just 3C. Doing that right now. I put the due date on it to be 7/11, which is Sunday. Our next class will be on Monday, the 12th. And so try as hard as you can, folks, for those who are behind, to get caught up through 3C. And on Monday, I'm going to finish chapter 3 and assign the chapter 3 test. Well, the quiz and the test. And we're moving on into chapter 4 next week. And so that is our game plan for the rest of this week and then going into next week. So next week we will be in chapter 4. And then it will be actually short-lived, just 2 sections on it. So by the next week, we will be in chapter 5. And then the hope is by the week after that, we will have to touch on chapter 7. So any questions? All right, so work real hard. And if so second. Okay, so if there aren't any other questions, I'm going to go ahead and let y'all go. And I will be back here at 1 o'clock for those who are in 120E or just want to come in for the class at 1 o'clock. So have a great weekend, and I will see you guys on Monday, unless I see you at 1 o'clock.
Thank you.
Thank you.